Hi, my name is Alia Batrisha binti Al-Kushari and my ID is 160048444.
Name is Najiha binti Azman, ID 17003014.
Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Zulaika binti Ahmad Mustafa. I am from Group 1M and I will be presenting for the last part.
In Chapter 4 of Modeling and Simulation of the Reactor in Stage 2, students are required to demonstrate a simulation of the reactor used in Stage 2. Our team has decided to simulate the process of steam reforming process, where it is a reaction between the methane and water to produce carbon monoxide and hydrogen. Using the Aspen HYSYS, we decided to select plug flow reactor as our reactor for this process. The objective of our dynamic mathematical model is to develop a model that enables the determination of density change along reactor length and time and the determination of species concentration profiles along reactor and time. Furthermore, the assumptions of this reactor is that the differential volume chosen sufficiently small such that there were no special variations in reaction rate within this volume, and the heat removed or added to the reaction efficiently to maintain the temperature inside the reactor. And lastly, the reactor tube is relatively small and fluid travel as plug flow, where variation only occurs along the reactor length. Firstly, we derive the mass balance. Since it is a steady state reactor, hence our mass balance is dP over dt equals to dPV over dL. Next, we derive the generic mole balance. Using the reaction of methane plus water to carbon monoxide plus hydrogen, we derive our rate law and rate constants. Rate constant is obtained from the manual calculations, which can be obtained from 4.3. After that, we derive our component A balance, component B balance, component C balance, and component D balance. After we derive our dynamic mathematical models, it is time to simulate the steam methane reforming process. And the steam methane reforming process can be seen as on the screen. So firstly, there are two feed flow rates that enters the mixer, where the methane feed stream and water feed stream enters at 700 degrees Celsius and 1000 kPa. The methane feed stream and the water feed stream enters the feed at 4758 kg mole per hour and 9516 kg mole per hour respectively. Then, the mixed feed enter the PFR SMR, where the reaction process occurs. The product of the steam methane reforming process is then enter the flash separator, where it separates the water and also the other product, hence increasing the concentration of hydrogen in the product itself. So, the water lives in S2 in liquid state, while the product lives in vapor state through S1. Hence, that sums up the steam methane reforming process simulation.
Next, after the simulation, we are required to validate the simulation by comparing with the manual calculation from Reaction Engineering 1. For this process, the required information is taken from the article. As you can see here, the temperature is ranged between 550 to 700, and we choose 700 degrees Celsius. The pressure is 1 atm, followed by reaction rate and activation energy. Now, we can calculate the reaction. With the assumption state at 4.2, we can determine the mole balance and energy balance. For exponential factor, it can be calculated from Antoine equation, and now we get 3.258 times to 10 to the power of 3 mol bar 0.5 over G dot S for the exponential factor. Next, build the stoichiometric table for SMR, which consists of characteristic, symbol, initial, change, remaining, and lastly concentration. For the conversion, we can calculate using equation and get the data from the article. Now we got 0.896 for the conversion. Then for stoichiometric value, we got 2, delta B equal to 0.01099, while delta C and delta D both is 0, and delta inert 0.0439. With the data get earlier, now we can calculate for the flow rate and also the concentration. Here is the result for FA0, FB0, FT0. Then FA, FB, FC, FD, Fi, and lastly, total flow rate. Then for the concentration, we calculate the CA0, CA, CB, CC, CD, CI. All of this is using the equation earlier at the stoichiometric table. After complete the reaction engineering calculation part, now we can calculate for deviation error. Deviation error consists of two, conversion and outlet flow rate. For simulation result, for conversion is 76.26% and for outlet flow rate is 21530 mole per hour. For conversion is 50% deviation error and for outlet flow rate 42% deviation error. It is almost same between the manual calculation and simulation as it below 50%.
The last part, we have to analyze and discuss the effect of pressure, temperature, and feed flow rate on reactor performance by using function case study in process simulation software and develop mathematical model. Now, we are looking for findings of effect of temperature, where we found that the higher temperature with constant value of frequency factor and activation energy that used in the kinetic reaction, the higher the conversion of the reactant to the usable product and the higher the concentration of desired concentration of hydrogen. Yes, and this experiment or in this simulation, we use 700 degrees Celsius as our temperature for both stream, methane and water. From this simulation, we are able to get the maximum hydrogen amount of 0.6958 at 700 degrees Celsius, while you only get 0.6604 at 500 degrees Celsius. This concludes that the higher the temperature, the higher hydrogen amount that we can get, and the higher the conversion also. Next, we go to the effect of pressure. What we have found is the higher the pressure with constant value of frequency factor and activation energy that used in kinetic reaction, the higher the conversion of the reactant to the usable product and the desired hydrogen amount. How we analyze is we use two different pressure for both methane and water streams. In this slide, we can see we use the atmospheric pressure equals to 101.35 kilopascal, and what we get is the conversion is higher. Also, the concentration of hydrogen is increased. The next slide, we can see the pressure is equals to 10,000 kilopascal or equals to 100 bars for both methane and water streams. The conversion also getting higher with the concentration of hydrogen also getting higher. Therefore, if we increase the pressure, we are able to get higher hydrogen amount and the conversion, but we have to limit it to 1000 kilopascal as it suits with the temperature previously, which is 700 degrees Celsius. Flow rate, we can see that in this slide, we double the flow rate for methane and water. Thus the conversion becomes 61.25%, which is lower than original, and hydrogen concentration also becomes lower. In the next slide, we lower the flow rate for methane. We just take 1000, and the flow rate for water you just take for 4758 kilogram mole per hour. But the conversion becomes 101.1%, which is this is impossible and not logic for our simulation, and the hydrogen also become lower. To summarize it, it can be concluded that as pressure increase, the temperature increase, the molar flow rate increase, and therefore the conversion will be increased.